Hello, everybody. So, over the course of this semester, there's been a couple of times where I've had to record a couple of supplemental videos for my application security or software exploitation course. Then I've posted them and made them public. It seems like there's people out there that are maybe interested in seeing that kind of content, and I figure since I have the examples available, it couldn't hurt to record them all, and that way I also have them available in a video for students in future application security / software exploitation courses. I do like recording them and putting them on YouTube whenever possible. Normally, of course, we record our asynchronous lectures with Zoom or Teams or something, and that's all well and good. It certainly facilitates asynchronous learning, but does not record usually in high def, so it can make sometimes demonstrations a little bit harder to see. So I do like having them recorded and up on YouTube where students can see them in HD if necessary. So what this is going to be is basically all of the examples from our CIS 311 application security course. So what we cover in that class is essentially a history of software exploitation and you know, basic attacks and defenses. I'm not going to go over, you know, source code review or secure programming practices or anything like that. I'm just going to focus on the examples of exploits here, beginning with simple buffer overflows. So let's get to it. So our first example here is a simple buffer overflow. Here's the source code on the right-hand side. As you can see, we got a main function that declares a 16-byte buffer. We have enter some data in a printf statement. We have a gets statement to fill buff. And then we have essentially just echoing back, you entered buff, whatever it happens to be in there. The issue in this case is that gets does not do any bounds checking. So while we have declared only 16 bytes for buff, we can grab more than that from the user, right? Let's run this quick and we'll see what we come up with. So there you can see, enter some data, and I'll enter just a couple bytes worth, certainly within the 16 bytes that has been declared. And it echoes it back, and it works exactly according to plan. If I enter more than that, let's see, we have, that certainly seems like it's more than 16 bytes to me. If we enter more than that, we get a seg fault. So, that seg fault is a clue that we have a bit of an issue potentially with the buffer overflow. That segmentation fault error essentially means that the program attempted to return, but for some reason or another, it did not find a valid return address. Let's use GDB here so we can see what's going on when we actually enter in this information. GDB, I'm running that with Jeff. It's a debugger. We're going to put a breakpoint on main, and we're going to run this. And it drops us in after the preamble in the main function. You can see down at the bottom in purple, the reason is breakpoint. We have stopped at hex 411A1 in main. So we are at main plus 8. So that's after the preamble, but before we actually get to any runnable code. We are right now at sub RSP hex 10. Hex 10 is 16 bytes. This sub RSP hex 10 is to make room for the variables that we have declared on the stack. We have a car declaration for 16 bytes. 16 bytes is a finite amount, so rather than needing to allocate any memory in the heap in an ad hoc fashion, because we have a finite amount of memory that is reserved, we can throw that right on the stack, and that's what we're doing. So from our current stack pointer, subtract 16 bytes, and that provides us with all of the room we need for our buff variable. The green, or I guess sort of bluish green, turquoise-ish color right here, that arrow there, that is our current instruction pointer. That is the instruction that is executing. So we have stopped on this sub. It hasn't quite executed just yet. Our base pointer and stack pointer reside together here at this memory address. You can see it's pointed out right here. So I'm going to hit NI for next instruction because we're going to execute that sub RSP hex 10. And when we do, we can see that our base pointer remains at that original address where that main function began. And we jump back 16 bytes. These are 8-byte memory addresses. So here is 8, 0 to 8, 8 to 16 right here. So 2 addresses. And now our stack pointer is at the top after that sub. 16 bytes away from where it began down here where the base pointer currently is. All right. Now we are here at load effective address. Our instruction pointer plus hex E8E, dropping us to this memory address, which is 40203A, which is going to put us past here, where we currently are. But that's just going to load that address into RDI. If we go up a little bit here, Jeff has our registers displayed for us. So RDI currently contains hex 1 right now. So let's next instruction and see what happens after we complete that load effective address. There we go. Now RDI contains that pointer 40203A, which points to the text that we have loaded in this printf statement for enter some data. Why is that loaded into RDI? Because the instruction that's executing right now is a call to the puts statement. I know it says printf here, but printf is going to use puts. And that code is currently at hex 401060, and when it executes, it's going to look for parameters that are being passed to puts in RDI. So basically, all that just happened is at 40203A, at that pointer, is some text. It's loaded into RDI so that when we load and execute code for puts, because we're calling puts, it's going to look in RDI for what text is meant to be printed, and that's how a print statement roughly works in the assembly instructions here. So let's go ahead and hit next instruction. We're expecting that to print out. It did. We are now, we used NI next instruction because we don't want to debug puts. So we just let it execute and jump past it so we can stay in the main function. Now we're at load effective address, LEA, into RAX, the value at RBP minus hex 10. We know what minus hex 10 is because we saw earlier that substatement. So we're loading into RAX the value that's currently essentially sitting up where we subbed before, which right now is nothing. We haven't run a get statement yet. Right now, RAX contains hex 16, or hex 10, sorry, 16. The hex value for 16 bytes. Let's next instruction, and we will see that now the value at RBP minus hex 10 is loaded in there, which is 0, but more specifically, it's the pointer value leading to where our stack pointer is, which contains the value of 0 right now. And we can see that the stack pointer is still there, but in addition to that, now RAX is also pointing to this top address here. Now we are going to load that value into RDI. Why are we going to do that? Because we have a gets statement coming up, and RDI is where we hold values for the parameter. So when we call RDI, we're basically telling gets where to put our input. So we're going to do that now. And now RDI, as you can see here, is also pointing to the top of our stack where the variable should be held, that buff variable. It's unfilled still because we haven't actually called gets yet. It's just setting it up so that we're ready to do that. Now we're going to move a 0 into EAX. EAX is the 32-byte version of the RAX register. So we're going to 0 that out. We're going to clean up RAX before we proceed with our gets. So we run that. Now RAX contains only A0. RDI now contains that pointer to where the buff variable begins. The stack pointer has not moved, neither has the base pointer. And now we are about to call that gets. Let's do that. Okay, now we can't see anything. It looks like the program has hung, but it's actually on that get statement. It's waiting for me to provide input. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8 A's and 1, 2, 3, 4, 5, 6, 7 B's. And I'm going to leave it there because I need one last byte for my carriage return. And I don't, at this point anyway, want to exceed 16 bytes. So 8 A's, 7 B's, and 1 carriage return. All right, and that puts us on the other side of the get statement where we're at an load effective address into RAX, the value at RBP minus hex 10, which is the top of our stack. And now we can see instead of zeros, what we have here at this pointer is the A's and B's that we entered. But we entered 16 bytes, and these are 8-byte addresses. So the first 8 bytes is basically just that, just our A's. It displays everything because this will display until it hits a carriage return. But this is all that address actually contains. We know because if we look at the second 8 bytes directly below that, the value that's being held there, it's not being ASCII translated directly. There's our ASCII translation, but hex 42 equals exactly what we see here, capital B's. So the first memory address is our 8 A's, the second memory address is our 7 B's and our carriage return. That's what happened to our input. Now I'm going to go ahead and I'm just going to hit continue here. And we're going to run that again, and this time I am going to enter too much data. Okay, so here we are again. There's our put statement again, and here is our get statement. Now I'm going to enter in 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And how about 1, 2, 3, 4, 5, 6, 7, 8, and a carriage return. So we're actually sending, or should I just go back? Should I just do 24? Or should I do 25? Let's do 24. I'm going to back off. 8 A's, 8 B's, 7 C's, and a carriage return. Okay, so what happened here? We can see the state of our stack here. This first memory address, just as before, contains 8 A's. The second memory address, just as before, contains B's, but now 8 B's. And the next address, which isn't part of our buff variable, it's actually our base pointer, is now hex 43434343, which is our C's. So we have overflowed our buffer. We have put in so much input that it extends beyond what was declared for our variable and actually overwrites our base pointer. But what is the significance of that? What is the base pointer? Well, at the end of a program, or at the end of any function, you're going to get a return. And when we call to another function, let's say from main we call another function, that other function runs, and then what does it need to do? It needs to return back to main at the exact location where it originally called that function so that it can execute any remaining code. At the end of a main function, we need that return essentially for the program to terminate, right? It's part of the epilogue. That return means that the program is done, exit gracefully. So what it's going to try and do, and this time we're going to step through it instead of continuing. Okay, so right now it's going to load the effective address. It wants to do that second print statement. You entered blah, blah, blah. So let's let it do it. Okay, here we go. Stepping it through, getting ready to do that print statement. You entered. This is the print statement here. So RDI contains you entered. RSI contains the text that we entered, and now that print statement's going to print it out. Okay, now at this point, what the program wants to do is exit. There's no more commands there's no more instructions. The main function is done. We are ready to get the heck out of here, right? We're ready to close this program out. So the first thing it's going to do in the epilogue is 0 EAX, which is where we are right now. Then it's going to leave. It's going to shut down the thread. Now it's going to attempt to return. Where is it going to attempt to return to? Well, our return address, our base pointer. But we get a seg fault because the address hex 43434343 is not a valid address to return to. So it just dies, right? I cannot return to that address, not a valid address. That's a segmentation fault. But what if that were a valid address? Even if it's not the correct address, what if it were a valid address? Well, let me hop out of GDB here for a second. And let's disassemble this binary. If we go to object dump, and you can see here in the source code, we actually have a function that is declared but never actually used. No way to possibly get here. And all it does is a print statement that somewhat resembles a shell. We're not actually going to pop a shell here in this case, but the principle is the same. Any code that would be here, if it were to, for example, call up in bash, it would execute. But since it's never called, how do we get there? Well, each of these functions, even if it's not used, they're going to be loaded into memory at runtime. That code has to reside on the stack. Even if it's not called, it has to be there because it's in the compiled binary. The compiled binary does not pick and choose what code gets loaded into memory. If it's valid and it's compiled, it's all part of the same binary, even if it's extraneous code. So if we look through here in our disassembly, here is the main function, right? And this binary does not take advantage of any modern security features. It doesn't take advantage of DEP or ASLR or any of that, which means that that memory address 401199 is where the main function can be found at every runtime, every time it executes. If we keep looking, here is the no way to possibly get here function. And that is always going to reside at 401176. It's effectively 23 bytes between the top of no way to possibly get here and main. So if that return address, instead of being junk data, if it happened to be an instruction to return to no way to possibly get here, to return to this address, it would hop right to it. I mean, that is what the instruction is saying. It says, hop to this return address, and the return address is overwritten, but it's a valid address, so it will absolutely do so. So if we use a tool like Pwn Tools, we can write something like this, right? Where we can grab the no way to possibly get here address, execute that process, overflow our buffer, 24 bytes, which we just saw as the beginning of our base function, the beginning of our base pointer, then follow that up with the pointer address to no way to possibly get here, and then go ahead and run that application, and when it returns, it will return to no way to possibly get here. And when we do that, here is the code being executed from the no way to possibly get here function. We have overflowed the buff variable and inserted our own return pointer over the existing base pointer, causing us to return to a function that was never actually called. What about our second example here? So in our second example, we have a main function and a SomeRandomThing function. SomeRandomThing, again, is never called, but all it does is declares an integer, my favorite number, 58623. The main function, again, gets some data and echoes that data back. Right? Let's go ahead and run it. Enter some data, AA, EBB. and just echoes it back, just like the first example. Now, in this case, we're not going to have it print out a shell. We actually want to execute a shell. In this case, we want to get a valid, stable shell from this exploit. So we have to ask ourselves, how are we going to do that? How do we create a shell or execute a shell when the compiled code doesn't contain a bin bash, it doesn't contain a debug shell or anything like that? Well, let's take a look at this disassembled code here again. See where we're at. So here's our main function, and we know that this doesn't contain the ability for us to add in or take advantage of a shell. We do have a get statement just as before with no bounds checking, so we know that we can overflow the 16-byte buffer again. Now, how do we take advantage of that? If we plug in the address for some random thing, we know that we can execute this code, but all this is doing is declaring an integer, and that's not particularly useful to us. That's not going to get us a shell. But if we look in some random thing, where is that integer declaration? Where is 58623 in this code? Well, we can see here we're pushing RBP, so we'll push our base pointer onto the stack. We move the pointer of where our current stack pointer is, that becomes RBP. Then we have this move, and we're moving to RBP minus hex 4, this value here. Then we have a NOP, which is no operation, so that does nothing. That's just for padding, alignment purposes. Then we have a pop RBP, so the base pointer, and then we have a return. That's all it does. So there's only one place where this number could reside, and that's right here, E4FF. Let's take a look at that. So E4FF, if we convert that from hex to des, that is 58,623. Okay, so that's where the number went to, right? The integer that's being declared is converted to a hex in our disassembled instruction. But what does that mean? Well, if you look at our assembly instructions, right here you can see that all of these instructions, push RBP, pop RBP, they correspond to byte pairs over here, because all applications are just binary. It's all just machine code. And byte pairs are just a way to represent in 1/4 of the space the binary of the actual application. And these instructions over here are just ways to interpret those instructions in a way that we can kind of understand, right? So we can see here that pop RBP is 5D. Let me show you a tool that we can use to do this conversion. Okay, so if I put that 5D here in an x86 disassembler, we can see that 5D right here translates to that pop EBP. In this case, again, the E register is just the 32-bit version of the 64-bit register. So while it says RBP here, EBP, RBP, but that is a pop. So what is it then if I put E4FF, the value that's being declared for that integer? What does that mean if we were to interpret those byte pairs as instructions instead of an integer value? So that translates to jump ESP. So essentially, jump to the stack pointer. The stack pointer is where we will be at the end of the insertion of our data. So basically, if we were to call this number as an instruction instead of as an integer declaration, what it would interpret it as is a jump statement back down to where we entered in our information. Meaning that if we overflow this buffer and instead jump to this exact location, not at the beginning of the instruction, but in the middle of the instruction, this exact address, then it would jump back down. And what might be waiting at that point? Well, potentially, because we can overflow this buffer, maybe it's some shellcode that we have placed on the stack. So when I say jump to the middle of the statement, that's because where the instructions are doesn't matter. The compiler wants everything to be aligned, but in terms of, calling addresses, it definitely doesn't have to be. We can call any address, even if it's not at the top, right? Because these are not fixed lengths. Look at some of these are longer, some of them are shorter, some of them are 1 byte pair, this one's 3 byte pairs. So if we take a look at this, we have 40117E, 40117F, 4011180, 4011181, and 4011182. So right here, 4011181, that's what we want to target here for the beginning of our instruction. And because it's x86, it's little endian, even though the value is E4FF to equal 58623, the actual value in memory is going to be little endian, so reverse loaded FFE4. So let's look at a potential solution here. So basically what we have here is shellcode that we're using Pwn tools to generate, right, for the appropriate architecture. We have the memory address for the beginning of the value, the integer value, that we are essentially going to be interpreting as an instruction to jump RSP. So then just like before, we can overflow that buffer by sending 24 bytes of jump data. We can overwrite RBP with the address to that jump RSP instruction, which will cause us to jump up to the some random thing to this exact location right here. So hold on, let me actually show you here. So here we are executing. Here's our get statement. Here's our return. So we're in the main function. The application runs as normal. We get to this location right here, and it says, okay, where am I returning to? Well, we have overwritten that address. So we return, and we actually jump up here. And that is being interpreted as a jump RSP. So we jump to RSP, which is going to be right after this statement. What will be sitting there? What instruction is sitting there after this statement? The shellcode that we have placed on the stack. Now, when I say that we're going to jump below this, it's not exactly the case, because actually when we overwrite this address, as we just saw with example 1, we're actually at the top of the stack, and we're actually flowing down past that. The instructions and the variables are actually held in slightly different locations. So when I say before and after, we're actually talking about 2 separate places, but in any event, conceptually, basically, we're jumping back to where we left off, to where we have placed the shellcode. Now, we don't need to worry about what the shellcode is. Pwn tools is taking care of that for us. We could print this out so I could show you what it looks like, or you can find any number of examples of shellcode on your own. There's plenty of them out there. Not important for this example. So let's run that. There we go. You entered some data, and we have an active valid shell. All right, so that's buffer overflows. That's essentially how they work. But this is 2 examples without any security whatsoever. The first thing that was implemented in terms of application security, the first measure that we have beginning in the late 90s, is what's known as a stack cookie. So let's talk about those next. All right, so stack cookies are essentially a security measure that was developed to protect applications from buffer overflows in the 90s. The idea is that at the time, at application runtime, a secret would be generated and placed on the stack. So essentially a randomly generated variable would be placed at the bottom of the stack between where the variables would be declared and where the base pointer could be found. And before a return was executed, there would be a check, and it would check the value that was originally generated for the stack cookie with the existing value of the stack cookie, and if they didn't match, it would kill the program, right? The cookie had to be validated in order for things to execute as they should. This is an option that is compiled into the application at make, or at compilation, right? So here, we're not using position-independent executables, we are using stack cookies. All right, so here we have an example that's pretty similar to our original, right? We have a 16-byte buffer that's being declared here. We also have an int here, 2 ints actually, that are being declared. That's because it's going to take our input, ask us to enter a string, ask us for a start position, ask us for a length, and then it will basically echo back the parts of the string that we have entered. So let's run it. I'll show you. So enter a string. So let's enter password. Enter a start position. How about 1? A length. How about 4? And it just echoes back the portion of our entry between where we started up to the length that we have entered. And it's going to continue to do that until we enter exit, where it does a string compare to determine whether or not it should quit. Right? Of course, it doesn't quit until after it runs until after it runs the segmenting, I guess, by the rest of the application. It's a little bit weird, but it is what it is, I suppose. All right, so we know that there's a stack cookie on there somewhere. I'm going to run this in GDB so I can show that process to you. Once again, I'm going to break main. We're going to run. All right, here we are after the preamble. We are at the top of the main function. So at this point, the stack cookie has been generated, but let's step through this so we can see where that comparison occurs, right? So here we are, we're subbing RSP hex 30. In this case, we have a 16-byte buffer. We know that that's hex 10, 16 bytes. So where's the next hex 10, or the hex 30? Where's that coming from? Well, we have 2 integers. Those are also going to be 8 bytes. We have 2 of those. That's another 16 bytes. So we're at hex 20. What about the last hex 10, the last 16 bytes? That's for our stack cookie. It has to go on the stack below the rest of our variables so that if we overflow them, we overwrite the stack cookie and the stack protector can kick in. So let's go ahead and jump up hex 30. There we go. We can see the state of the stack. We've got the base pointer there at the bottom, the stack pointer at the top, but none of those memory addresses currently are really in use. So let's keep going. We are now going to move a keyword pointer that is at FS hex 28 into RAX. RAX currently should be zeroed. It currently contains the pointer to main 0, but this will take care of that. Okay, so a single step, and now RAX contains this value right here. Again, this is coming. This is a keyword. So 16 bytes. That was at FS hex 28. What value could that possibly be? It's going to move that from RAX to the value at RBP minus hex 8. So here's RBP. Hex minus 8 is the memory address just above it. And there it is. That is our stack cookie. The FS hex 28 is where it was essentially generated. We moved it from where it was generated into RAX. We moved it from RAX into the space that was reserved for our variables, in this case placing it just above the base pointer to protect it. How do we know it's the stack cookie? Well, other than the fact that it's, not a variable that we have entered, it ends in 0, 0. Stack cookies always end in 0, 0 because the idea is that if there is a memory leak, like for example, we have a scan or a print statement or something that's going to read the stack or variables in the stack, it will stop before the stack cookie is leaked because it'll hit that 00, and a null byte is a terminator for a string when we're interpreting it. So they always end in 0, 0. So number 1, the way it looks like a randomly generated value. Number 2, its position. It's right above the base pointer. That's where the stack cookie goes. Number 3, it ends in 0, 0. I know that this is our stack cookie. Now we are going to XOR EAX with EAX, which means we are going to zero it out, and that will essentially get rid of that copy of the stack cookie in RAX, and it will reside only there in the stack just above RBP. And now we are basically moving on with the rest of the application as we saw before. So we're going to have a print statement. It's going to ask us to enter a string. Okay, there's our print. Here comes our scanf, where it's actually going to gather that information from us. Enter a string. How about I enter 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and a carriage return. All right, now it's going to ask us, you can see it's placed it on the stack there, A, B, 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 C, 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 etc., etc. It's long enough that it's using up both of the reserved addresses for that. Okay, let's keep going, and now it's going to ask us for a start position. Okay, there it is. I'm going to start at position 0. And now it's going to ask us for an ending position. There it is. If I were to ask for, let's say, way more bytes than I've actually entered, how about 32 bytes? And now it's going to do the puts, and it's going to print that back out for us. Now it's going to move into EDX RBP hex 28 minus hex 28. Load effective address RBP minus hex 20. And here's our write statement. And there's our string compare, checking to see if it is the word exit. But here is what I wanted to show you before. If it were exit, this would be the end of our program, which means that it's going to hit that final return. This is the check that it's doing to see if the stack cookie has been tampered with in any way. We move the value at RBP minus hex 8, which is the stack cookie right here. We compare that with the version of the stack cookie that was originally created at FS hex 28 by XORing it. If the result is 0, then the value that was generated is the same as the value that was placed on the stack, and therefore it works. It's valid. If it fails that comparison, then the stack cookie has been tampered with, and we exit. The program crashes. Okay, so actually, let's see what that looks like if we run it instead of running it in the debugger. If I enter a value that is way too long, that is definitely going to blast past our stack cookie. Start position 0, length 128. It loops because it wasn't the value exit. So it never reaches the end of the program and thus never validates the stack cookie. But if I do enter exit, start position, end position, stack smashing detected. That means that the stack cookie validation check failed. But also, look what came back when it echoed back that data, when I asked it to essentially provide way more output than I actually provided. 128 characters in this case, or 128 bytes, we have something here at the end that's not information that I entered. That's data that's on the stack. It's just not a printable ASCII character, so we just get the question marks. So, in order to defeat stack cookies, there's two things that we can do. In this case, that data that's at the very end is possibly our stack cookie. It's there just below the variables. So if we can get past that null byte terminator, we could leak the stack cookie and then just put it back where it belongs, and then proceed just as we did with example 2 with our own shellcode. It will pass the validation because we're putting it back where it belongs before we start inserting more malicious code. So if we look at the solution here for example 1, essentially what we can do is we can enter some junk data. It doesn't have to overflow. But when it asks us for a start position, we give it a start position that is actually past the memory space that is reserved for the buffer. We ask it to start reading at the beginning of the stack cookie instead of the beginning of our input. Then we ask it to read 8 bytes. So print out 8 bytes. That will essentially print out our stack cookie. If we can then read those bytes, put them into a variable here called cookie, then all we need to do the next time it loops around is overflow the variable for buff, put the stack cookie back where it belongs, and then put any old data that we want on the stack, and we have completely bypassed the stack cookie. Alright, so now in this case I'm just going to send B's and C's instead of doing shellcode or anything, but we're going to attach this process to GDB in our script so that we can see exactly how this all ends up in the end, okay? And then we just finish that up just by exiting the program so that it can end, and if B and C, if we were doing something other than just putting data on the stack, then we could return then to maybe a ROP gadget or something after that. Now, stack cookies are also only protect certain types of meddling, stack smashing. It is entirely possible to continue to exploit an application and the stack cookie never comes into play at all. Like in this case, we have a simple application that asks us to enter the password. Let's go ahead and run it. Enter the password. What if I enter test? Incorrect. Okay. Well, we have access to the source code, so we can see that the password is secret in this weird camel case type thing, right? But presumably it wouldn't be quite that easy if we had compiled it, but we can take a look at this through object dump, and just like we saw the integer value in the second buffer overflow example, we can see there is a value here which we can convert, right? And again, little endian, so first in, last out, it's secret backwards. So we can figure it out like that, right? And if we were to do something like that, and if we were to have an information leak, right, the stack cookie doesn't even come into play in this case, because we have other vulnerabilities with this application that are just irrelevant to meddling with the stack, right? So the first bit of security that was placed over applications in the late 90s did something. It is still around. It is still a good thing to do in order to avoid those easy stack smashing vulnerabilities, but it's not the end all be all, not by a long shot. Okay, I think that we're at about an hour here, so I'm going to continue this into a part 2, where we will talk about the next 2 advancements in application security, which is data execution prevention and address space layout randomization. So if you are interested, we'll see you on the next one.